Recently, a game called Mario Kart Tour was released on the App Store. I downloaded it so I could analyze its computational complexity. The game, at least the racing mode, is P-space hard. First, let's go over the rules of the game. Mario Kart Tour is a multiplayer racing game. There are different modes, but we will focus on the racing mode. A race takes place between m different players on a track T. A track can have varying length and items that players can pick up and use. The relevant items we will consider are bananas, denoted by B, and green shells, denoted by G. A player who hits a banana is temporarily slowed down. A green shell can be used by a player to hit a banana out of the way. There are many other items and track properties, but we will not need them. The player who reaches the finish line first wins. We define the Mario Kart problem as follows. Given a track T, can player P force a win? Our proof strategy will be to show that QSet reduces to Mario Kart in polynomial time. In other words, we will show how to convert any instance of QSet into an instance of Mario Kart. Since QSet is a known P-space hard problem, it will follow that Mario Kart is also P-space hard. Before we do the reduction, let's first go over what QSet is. QSet takes in a quantified Boolean formula and outputs 1 if it is satisfiable and 0 otherwise. For example, consider the following quantified Boolean formula. For all x, there exists y such that x or y and not x or not y. To answer this question, we need to consider two cases. Case 1, x equals 1, and case 2, x equals 0. In case 1, x equals 1, the first clause is automatically satisfied. In the second clause, we can set y equal to 0, and then it is satisfied. So in x equals 1, the formula is satisfiable. In case 2, we have x equals 0. In this case, the second clause is automatically satisfied. Then, in the first clause, we can choose y equal to 1, and then the whole expression is satisfied. Therefore, for all x, there does exist y, such that the expression is satisfied. So QSat of phi equals 1. But we can think about QSat in a different way. We can treat it as a game with two players, U and E. U sets the universal variables, that is, the ones preceded by for all, which in this case is x. E sets the existential variables, those preceded by there exists. In this case, this is y. The players take turns setting the variables in the order of the quantifiers. Player U wins if the expression comes out false, and player E wins if the expression comes out true. In this framework, we can rephrase QSat of phi as the function that outputs 1 if and only if E can force a win. In this case, no matter player U's choice of x, player E can choose a y to make the expression true. Therefore, E can force a win, so QSat phi equals 1. Now we are ready for the reduction. Given a quantified Boolean formula, we will set up a Mario Kart race as follows. We will have two racers, U and E. Each will have its own track, and U's track will be slightly longer. We will see why this is important later. The track will consist of two main stages. The first stage is variable assignment. I will describe a specific variable assignment gadget later, but the overall idea is that for each variable, it will pass over all the clauses that the variable is involved in, and player E will be equipped with green shells, while player U will be equipped with bananas. Player E will clear bananas from the clause paths that it wants to go on, which is equivalent to setting a variable to true or false, and player U will throw bananas onto paths, the equivalent of setting a variable to true or false. In between the two main stages, there will be a clear stage, which clears E's items so that when E passes through the clauses, it is not equipped with shells and is able to clear paths that it should not be able to clear. It will be clear. Stage 2 is clauses. If there's a satisfying assignment and the variables are set in such a way that there's a clear path for E to travel on, then E wins because it has a slightly shorter path. However, if the variables are not set properly, E will end up hitting a banana and will be slowed down by just a little. We will construct the clause paths so that even if E is slowed down by a little, U will win. Now let's formally define the gadgets. We will start with the clause gadget. The setup is like this. For a clause with n variables, the path will split into n equal length paths. Existential variable paths will start with bananas on the paths, while universal variable paths will start with nothing on the paths. Once again, let's consider the example that we used for QSet. There will be two clauses and they will look like this. Note that the existential variables start with bananas on the paths, but the universal variables have clear paths. From now on, we will denote a clause gadget like this. The next order of business is the variable gadgets. For a given variable x, the path will split into two equal length paths representing x and not x. Each path will pass over all the clause paths that involve the variable. If x is an existential variable, there will be green shells along the path that the player can pick up and use. If the variable is universal, there will be banana items along the path that the player can pick up and use. In the case of player E, E clears bananas from paths it wants to go on. This is equivalent to setting its choice of x or not x to true. Otherwise, it stays false. A clear path corresponds to a variable with a true value, while a false path corresponds to a variable with a banana blocking it. For player U, U sets x or not x to false by throwing bananas onto the path. From now on, we will denote variable assignment gadgets like this. For the clear gadget, we just want to make sure that E does not hold any shells while passing through the clause gadgets. Since a player can only hold one item at a time, we can accomplish this by putting a green shell item followed by a banana blocking the path. In order to win, E must not be slowed down, so it must use the green shell item to clear the banana from its path. Then E will be empty-handed as it leaves the clear gadget. To better understand how this works, let's consider how we would apply this on our friend Phi. Player U makes the first move. U chooses X or not X and throws a banana to set one of them to false. Player E goes next. After U's choice, one of the two clause gadgets will have bananas blocking both paths. In order to win, E will choose the variable that corresponds to that clause and clear the banana from that path. Now E passes through the clear gadget and comes out empty-handed. E then drives through the two clause gadgets, taking the paths that have been cleared. Notice that E will only have a clear path if Phi is satisfiable. U takes a slightly longer path. This is denoted by the winding path. In this case, E can force a win because its path is shorter. Therefore, Mario Kart applied on this game returns 1. Now we understand how this reduction works, but we can still add a few more assumptions to make the reduction more precise. First, all the paths have walls, so players have to stay on their own tracks. They can't jump from variables to clauses as they pass over the clause paths. However, the walls will be low enough that bananas and green shells can still be thrown over them. This is possible as shown by the screenshot of me hugging the edge as I throw a banana over the edge. Our second assumption will be that both U and E are playing optimally and they are going at maximum velocity the whole time. This ensures that E, who has the shorter path, will always win as long as they don't hit a banana along the way. Our final assumption will be that both players can see all the clause paths at all times, so they know the actions of the other player and can make an informed decision about their own. Now for the runtime analysis. Each gadget has a constant size, so altogether they can be made in linear time. It follows that connecting all of these gadgets takes at most linear time. Finally, we want to make the universal player's path slightly longer than the existential player's path. We can tweak the path by scaling everything up and adding a few sections, which will take at most polynomial time. Overall, this reduction takes at most polynomial time. So there's a polynomial time reduction from QSat to Mario Kart. Hence, Mario Kart is p-space hard. As Julius Caesar would say, quod erat demonstrandum.